Our goal in this next activity is to look at the motions of a pendulum and then a Ferris wheel, and to be able to graph and write equations that would represent this parametric motion. So consider the pendulum below. The pendulum itself is 1 foot long. So if we start with that piece of information, we know then that that means that this length of the pendulum itself is 1 foot. Keep in mind that that 1 foot applies to the pendulum no matter what location it actually falls in. So these are all 1 feet. We also know the pendulum has a period of 2 seconds. And what that means is that it's going to take 2 seconds for it to complete 1 cycle. 1 cycle would be the amount of time it takes for the pendulum to swing backwards in one direction from point A to C and then to return again to point A. So that entire time is going to take 2 seconds to complete that 1 circuit. It then tells us that at t equals 0, the pendulum is located at point A. So this point right here, keep in mind that that is when t equals 0, so that's where the pendulum is starting. And point A is 30 degrees from the center line. So this angle right up here is an angle of 30 degrees. Now, we're going to try to graph this situation by placing this pendulum on a coordinate system where the origin is going to correspond to point B. So I'm going to consider, and let's kind of change the colors here. Okay, so I'm going to consider this kind of on a coordinate system. We'll draw a large y-axis and a large x-axis where the origin is at that point B down below. Now, it does give you a hint to look for a right triangle. So if you look back at our drawing, you can kind of see that we can make a right triangle right in here. The angle right here where the horizontal and vertical meet is a right angle. We have a 60-degree angle at the top, which means that this would have to be a 60-degree angle at the bottom. Now, by using this triangle, keep in mind some of you might recognize this triangle as a 30, 60, 90 triangle that you learned about way back in geometry. And one of the things we learned in a 30, 60, 90 triangle is that there's a relationship between the sides. You always look for the 30-degree angle, which is our smallest angle. The side across from that is A. The hypotenuse is 2A, and the third side across from 60 is A square root 3. So if we apply that pattern, we are given the hypotenuse here is 1. If the hypotenuse is 1, then the side across from 30 will be half of that, which means that this horizontal distance is 1/2, and the side across from 60 will be 1/2 times root 3, which means this would be 1/2 times root 3. Now that's one option. The other option, if you've forgotten those special right triangles, is to just think about your trig calculations. Again, if we knew that we had an angle up here at the top of 30 degrees, we knew this side was 1, and we were trying to find this distance, we could do the sine of 30 degrees equals the opposite, which is x, over the hypotenuse, which means the sine of 30 degrees is x. So what is the sine of 30 degrees? Well, the sine of 30 degrees is 1/2. So we could use those trig functions to solve for both the x and let's call that the y value. We could do the cosine of 30 degrees equals the adjacent over the hypotenuse. Therefore, to find the y value, I need the cosine of 30 degrees, and that's that square root 3 over 2. So two different ways that we could find those values. Now, why do we need those values? Because if we go back, we want to remember that we can now identify some key ordered pairs. Remember, we were trying to plot this on a coordinate system. So let's think about ordered pairs. If I wanted to know the ordered pair at point A, keep in mind that my horizontal distance is 1/2, and because I've moved to the left, that horizontal distance is actually negative 1/2. Add that negative in here. Now the vertical distance, be careful, the vertical distance is not the root 3 over 2. The vertical distance is the distance from the origin up to that 1/2. Well, remember that the pendulum itself was 1 foot long. So to find this distance, I'm going to take that 1 foot pendulum and I'm going to subtract the top part, which is square root 3 over 2. And if I do that subtraction, that's going to end up giving me, throw that in our calculator here, that would end up being 1 minus, in parentheses, the square root of 3 divided by 2, and we'll close those parentheses. So that's going to give us about 1.3 if we round that. So I'll go ahead and put that 1.3 now. Okay, so now we've got at least one ordered pair. Let's think about the path of the pendulum. We're going to use the path of the pendulum now to make a bit of an input-output table at some different points. So if I slide this over a bit, let's think about our parameter, which is our time, and what we're going to do is compare the x values and the y values at any given time. So for example, when I'm at point A, okay, that was time 0, so at a time of 0 at point A, my x was -1/2 and my y was 0.13. That was the ordered pair that we just came up with. Okay, then my pendulum moved to point B. Well, how much time passed? Since we know that it took 2 seconds to make it all the way down and back, then this was halfway in one direction, which means at point B, we have gone half a second, excuse me, and at point B, we're at the origin, which means x is 0, y is 0. Okay, then if we go another half a second, now we should be at point C. So at point C, we've gone another half a second. And this time, think about the ordered pair. We are now to the right of the origin, so we are now 1/2 away. And our y value, you'll notice we're at the same height as the other y value, so our y value is still going to be 0.13. So at my point C, I have an x value of 1/2 and a y value of 0.13. Then I'm going to make my return trip. So now I'm going to return to point D. It's been another half a second, which means it's been a total of, you know what I just realized? We don't want to write 1/2 again. We want to write the full time. Okay, it took 1 second to get all the way to point C. Then it took another half a second to come back to point B again. So now I'm at 1.5 seconds, and I'm back at 0, 0. And then it's going to take me another half a second to return to my starting point. So now it's been a total of 2 seconds. And at my starting point, I'm back at -1/2 and 0.13. So we're using our graph, our picture, excuse me, to make this table. Now what we're going to do is create a few graphs from that table. So the first thing that we want to graph is x versus t. Now, when we graph x versus t, keep in mind we're using the information from the chart here. I'm going to zoom in a little bit so we have some more room. We're going to be plotting, or graphing, excuse me, this key information, x of t. T is our input variable, and x in this case is our output variable. So do be careful on how you're labeling this graph. Okay, looking at all of my x values, I can see that my x-axis, which again is my vertical axis, I have to go from -1/2 to +1/2. So I'm going to come down here to -1/2, 0, +1/2. Now my t values, I'm going to have to go from 0 to 2. So we'll do 0, 1/2, 1, 1.5, and 2. And I'm just going to be plotting those points. At 0, I'm going to be down here at -1/2. Then at 1/2, I am at 0. At 1, I am at +1/2. At 1.5, I'm back at 0. And at 2, I am back down at -1/2 again. And if we sketch that, we see kind of a curve that looks like this. Now keep in mind, this is one period, which means that the pendulum is going to continue to swing out and back, which means that this will continue to follow in this pattern. So from this graph, now we're going to try to write the equation of this curve. Now, hopefully, we all recognize this curve as maybe an inverted cosine curve. Our traditional cosine graph looks like this, starting up here, kind of dropping low, coming back up again. So this appears to be kind of an inverted cosine graph. Now, if we think about writing the equation, remember that when we're writing equation for cosine or sine curves, we want to look for that a value. It's either going to be sine or, in this case, cosine. We need a b value. We need to look for our angle. In this case, our angle is the variable t. That was our input. We need to look for a c value, and we need to look for a d value. So where are these values coming from? Well, looking back at the graph, some key things. One of the things we talked about was the midline, and the midline helps us determine the d value. Since our midline is at 0, that means that the d value is also 0. You could write the plus 0, or you can leave it blank. The a value, remember, was the amplitude, and for the a value, we're going to look at the distance from that midline up to that highest point or to that lowest point. So we're looking at an amplitude of 1/2 for our a value. And keep in mind that because it was inverted, we know that this is going to be a negative a value. So now we have this much so far. Okay, the b value of our graph, we can find the b value by doing 2 pi and dividing it by the period. Remember that the period of this graph was 2 seconds. That was given at the beginning. So 2 pi divided by 2 gives us a b value of pi. So now I've got my b value. We know that we were looking at the variable t as our input. The c value would be any horizontal shift that we either added or subtracted. Well, again, since the graph started on that vertical axis, there was no horizontal shift. So again, that c value is also plus 0. You can write the equation with or without those zeros. So if you wanted to keep it simple, you could just say negative 1/2 cosine pi times t for your equation. So now we're going to come back and we're going to do the same thing, but this time we're going to be doing a graph comparing our y versus our time. So looking back, we're going to be using our time our time variables, but this time we're going to be using our y variables to be able to plot these points. Okay, again, you'll notice that your y-axis is your vertical axis. Our input is our t value, so that t is the horizontal, and our t value still goes from 0 to 2. So I'll put in that 1/2, 1, 1.5, and 2. Then when we start plotting our points, our y values, now our y values are only going up to actually 0.13. So we go 0, our highest point is 0.13, and we don't have any negatives. So if we plot this, starting at 0, we were at 0.13. Then, sorry, kind of zoom out here for a minute here. Then we had at 1/2, we were at 0. At 1, we were back up at 0.13 again. At 1.5, we were back at 0. And at 2, we were back up at 0.13 again. So it appears that our graph is kind of doing one of these. And now we need to write an equation for this one. Now we can look at this a couple of different ways. What you want to do is focus in on one portion of the graph that has an inverse. So in other words, it has to pass that horizontal line test. I would focus on, and again, you can kind of make some choices here, but you want to focus on kind of one part of the graph, something like this. If you extend beyond that, you're going to end up with a part that won't pass that horizontal line test anymore. Okay, so what is this? Well, once again, this appears to be a cosine graph, not inverted this time. Cosine graphs do start high. This one does as well. So just like the last one, we need an a value. We know it's a cosine. We need a b value. Our variable is our time. We need a c value, and we need a d value. And again, we already know that it's a cosine, so I'm going to put the cosine in here. Okay, let's start with that midline again. We need to determine this time where that midline is. And we can figure out where that midline is by finding that midpoint. So if we do 0.13 minus 0 and then divide that by 2, we should end up with a midline of about 0.065. And keep in mind that that midline of 0.065 is actually representing the D value. So I'm going to come down to my equation and I'm going to add 0.065 for my D value. Next, I'm going to come over and find my amplitude. My amplitude then is the distance from the midline up to that highest point, or from the midline down to that lowest point. Well, my lowest point is 0, so that means my amplitude is again 0.065. B value, remember to find the B value, we'll do 2 pi divided by the period, which was 2. So my B, sorry, I take that back. The period is not 2 on this graph. The period on this graph is only 1. So we're going to go back, and our B value is going to be 2 pi divided by 1, giving us a B value of still 2 pi. So I can plug that in. And again, my variable is t. My c value is my horizontal shift. And since I did not shift this graph to the left or right, there is no c value. So that concludes my equation for y of t. And then the last thing we're going to do, now that we have these two equations, is we're going to look at graphing these two equations, both on a graphing calculator or on Desmos, and kind of looking at that motion of the graph as it turns. At this point, before we actually graph these, we're going to save the graphing until we're together in class. What I would like you to do is to pause the video and take a moment to try the first problem, the first practice problem on your own from in our notes. Now we're going to be modeling the motion of a Ferris wheel, doing a very similar process. So this Ferris wheel has a 40-foot radius. Now again, consider that 40-foot radius. That means that from the center of the Ferris wheel in any direction is going to be that 40 feet. And I'll just kind of mark a couple of those just to kind of keep that in mind, that radius is in any direction. It makes 1 revolution every 40 seconds. So we do know how long it takes for it to complete 1 cycle. At t equals 0, you board on the lowest point of the wheel. So t equals 0, our boarding point is going to be right here. However, it does say that this is 5 feet above the ground. So the distance from here to here is actually a distance of 5 feet. Obviously, we're not on the ground at the moment. Now, it says set the center of our coordinate axis on the ground below the boarding point. So let's say that the center, if we kind of envisioned a coordinate, an xy axis on here, we're going to position 0, 0 right here, right below the boarding point. And just like we've done in the previous example, we're going to make a table of values to compare the position of the Ferris wheel along different periods of time in its cycle. So for example, at a time of 0 seconds, where would the Ferris wheel, where would the Ferris wheel be on a coordinate grid? What would be its x and y position? Well, keep in mind that at 0, 0, so keep in mind that at the point 0, 0, I'm going to switch colors here real quick. At the point 0, 0, at a time of 0, this is when you're actually boarding the Ferris wheel. And if you consider this point as an ordered pair, you're 5 feet above the ground, but you're at a horizontal distance of 0. So this is going to be the point 0, 5, which means that at 0 seconds, your position is at the coordinates 0, 5. Now, if it takes 40 seconds to make 1 rotation, then that means that if we go a quarter of the way, that's going to be 10 seconds. Halfway around, that's 20 seconds. 3/4 of the way, 30 seconds. And back to 40 seconds returns us back to our starting position. Okay, so what's happening at 10 seconds? Well, at 10 seconds, we're going to be over at this location. So now we need to figure out the exact coordinates on a coordinate grid. Well, since the radius is 40, we know that we have gone horizontally 40 feet at this point. And then in terms of the vertical distance, remember the radius is still 40. However, we started 5 feet above the ground. So if we put that together, this vertical distance is actually 45, meaning that at 10 seconds, our position is now at 40 and 45. And we're going to do that all the way around the clock. Right here, when we're at the top of the Ferris wheel at 20 seconds, our horizontal distance is 0. But if we put together our vertical distance, we have to include the radius of both radii of 40, so a diameter of 80, plus that height of 5 feet, which means that we are now at a height of 85 feet above the ground. So this is 0, 85. Over at a time of 30 seconds, we're just going to be in the opposite direction. So this means that we are at negative 40, but still 45 feet above the ground. Negative 40 and 45 feet above the ground. And then after 40 seconds, we are back to our starting location, which again, remember, was 0, 5. So now with this information, we are going to sketch a couple of graphs. The first one we're going to sketch is a graph of the time compared to the x position. So we're going to be graphing these two, and that's x versus t. Okay, keep in mind that our time is our input value, so I'm going to be on my time axis, I'm going to be going from 0 to 40. So I'll do 10, 20, 30, 40. And then my x-axis, those are going to be my output values. For my output values, I need to go from a negative 40 to a positive 40. So I'm going to have negative 40 down at the bottom, positive 40 at the top. And then we're going to plot these points. I'm going to switch colors to plot the points. We'll do that in green. So at a time of 0 seconds, we had an x position of 0. At a time of 10 seconds, we were at a height of 40. At 20 seconds, we were back at 0 again. At 30 seconds, we were down at negative 40. And at 40 seconds, we were at 0 again. So here is our graph of this motion. And now we can do the same process for the time versus the y position. So this time we're going to be looking at time. Oops, I apologize for that. We're going to be looking at the time versus the y position. Again, our time is still going from 0 to 40, so we'll still do our 10, 20, 30, and 40 on our input axis. Our y values are going from a low of 5 all the way up to an 85, so I'm just going to make sure that I get that 85 up here. Let's go ahead and throw the 45 on here, and we can go ahead and throw the 5 on here as well. And then if we plot these points, again, I'll do that in green. At 0, we were at a starting height of 5. At 10 seconds, we were at 45. At 20 seconds, we were at 85. Then we were back at 45, and then we were back at 5 again. So this represents our time versus our height. Now with these two graphs, we now want to be able to write the equations. And again, that just goes back to what type of trig graph is this. This first one is resembling a sine graph, whereas this one is resembling an inverted cosine graph. So I'm going to say it's a negative cosine graph. And we're looking for those key values in our equation, the a, b, c, and d values. So as we go back through this first one, we know that this one is a sine graph. We're looking for the A, the B, the C, and the D value. A value, our amplitude, since it does show that our center line, or our midline remains at 0, our amplitude then is from the midline to the highest and lowest points, which means our A value is still 40. I'm going to throw that in for the A value. And since the midline is at 0, that means that our D value is technically plus 0, which we can include or not. The B value is related to the period. So to find the B value, we're going to do 2 pi divided by the period. And the period, recall, is 40 seconds. So 2 pi divided by 40 gives us a B value of pi over 20. Okay, keep in mind our input value is t, so I'm going to go ahead and throw that variable t in there. And since our starting position is on the vertical axis, that means that we did not shift horizontally, so there is no c value, which means that my equation can be left like this. So here is an equation. I'm going to leave out the +0 that would represent the sine graph. Looking over at our cosine graph, this one we decided was a negative cosine graph. And again, we're going to look for our A, B, C, and D values. Excuse me. In this case, our midline is not at the 0, 0 anymore. Our midline is right here at 45. So we know right away we do have a D value of +45. The A value, the amplitude, is the distance from the midline to the highest and lowest points. So that A value is still 40. I'll throw in that 40. The B value hasn't changed because the period hasn't changed. It's still a period of 40 seconds. So our B value is still going to be that pi/20. I'm going to throw in our variable time. And again, since we did start on the vertical axis, there's no horizontal shift, so there is no C value this time, which means that our final equation is this one. So then, of course, the next step would be to graph these equations to model the actual motion. And again, we're going to show that when we return to class.